Okay, so we're building up an intuition for how, if we have a bunch of different charges, how they will actually have forces on each other. And ultimately, those forces might be connected to motion. But at the moment, we're just wondering about if I have a collection of charges, how is that going to be pulling another charge? And so let's try to build up a little intuition. We're going to be continuing with using Coulomb's law here, but we're going to generalize it in just a moment, because thinking about this force, right, we covered a force between two different charges. What if we had three charges or more? Then what would we do in this kind of situation? Well, that's where we introduce an electric field. So our electric field is actually defined as the force per charge. Or in other words, we could actually say that if I calculated the electric field, then all I would need to do is put in the charge that I'm interested in calculating some force, and then I would be done. So in other words, I could calculate the electric field in that previous scenario as kq1 over d squared, and that would be my electric field. And if I wanted to figure out what the force was, I could actually say, and that would be, I guess, in this case, in the minus x hat direction, plus x hat direction, then I could actually just put in the charge. Just to remind you, the problem that we were working on earlier was a plus charge and a minus charge. And so if I calculated the electric field at this location here, I'd find that the electric field points in the positive x hat direction. But now, by multiplying this electric field by the charge Q2, then I can actually find the force on that charge. So in other words, I have kq1 over d squared in the x hat direction multiplied by the charge, which we decided was a minus q. This one was a plus q. So I'll have my minus q here. And again, we recover the same result, which is the force is equal to, in other words, that the force is equal to kq squared with an overall minus sign over d squared. So in the x hat direction. So, or in other words, you could say it's magnitude kq squared over d squared in the minus x hat direction, right? So in other words, the result's the same. So you might think, well, okay, we've just done some fancy dance and we haven't really gotten anywhere yet. So, but this is actually very helpful for us, because I can see that if I have this positive charge and this negative charge, that the overall force on this negative charge is in this direction, okay? So now, actually, what if I put a third charge over here? Well, if you ignored this charge for just a moment and you said, okay, I'm interested in calculating the force between this positive charge and this negative charge, well, it also seems like a pretty straightforward scenario. I think you know that they're going to attract. But now we have two forces on this thing here, so we could actually calculate the composite force. This is one way to go about things, but we're going to actually generalize. And for the moment, we're actually not going to worry at all about the fact that there's a minus q right here. In fact, what I'd like to do for the moment is just to calculate the strength of an electric field right at this location. So to make it kind of a good example scenario here, I will have some distance d here. That's the distance laterally here. And then I'll also have some distance d going across here. So here's my distance. And I want to calculate the electric field at this point. And that way, if I wanted to put a charge there, I could figure out immediately what the force is. So I'm going to go ahead and erase this here. And I'm going to be thinking about what is the what is going to be the electric field here at this location. So we can use our sort of modified Coulomb's law now, and we can say that, okay, it looks like I'm going to calculate the electric field at this location from this charge, and the electric field at this location from this charge. So I can actually say, okay, then the electric field total is going to be equal to the electric field from the first charge. Let's call this, let's give them some names here so that we can see what they are. So Q1, for example, I'm going to call this one Q3. And if you remember, we had Q2 that we're going to potentially put over here. So we have electric field from this Q1, electric field from this Q3, and we're going to try to figure out what each of those electric fields are at this location here where I've drawn an X. Okay, so basically it looks like I'm basically writing this thing here, but I'm ignoring the Q2. So in other words, each force per charge is just going to be K, Q, and I'm going to write of I. So this is going to be the force because of each ith charge, where I could be 1 or 2 or 3 or so on, divided by the distance squared, in the vector direction that connects the charge to the point that I'm interested in. Okay, so that seems pretty straightforward, and I'll actually write kind of an I here to remind me about that matters, and also that this distance here is also mattering. So that maybe this is the distance that connects in this case. So I could maybe write it more generally here as this script R, as meaning that this vector that connects between this charge and this point here. And then I'm also interested in the length of that, which I'm going to divide by the length squared over here. So, okay, so it seems pretty straightforward now. We've set the table, and I can write, according to this idea here, that the electric field at this point here, as we calculated before, was just KQ1 over d squared in the positive x hat direction. Maybe I should write also my coordinate system here, which I could write, for example, here's my x, and here's my y. So what about the electric field from Q3? Well, I could write again plus KQ3 over d squared, remembering that this is the same d in this case. It could in general be a different length. And, but this time, the vector that connects Q3 to this point here is pointed in the y hat direction. So I'm actually going to put the y hat direction now. And so I can combine these things. So for example, let's say that Q3 is equal to a positive Q, and Q1 is equal to a positive Q. Then I can combine these results here, and I can say that this is equal to KQ over d squared. And it looks like both of those are KQ over d squared. So then I can just simply write x hat plus y hat. So if we were to add up the two vectors, in other words, we have the contribution from Q1 points in this direction, contribution from Q3 points in this direction. So if we were to add those two vectors together, we'd actually say, okay, we could put them tip to tail, and I could do something like this, and then the resultant vector is the addition of the two. So in other words, this is my resultant vector, which is the x hat plus y hat. So this tells me the direction of the electric field. Now, does it tell me the same thing as the direction of the force? Well, close, but we have to pay attention to what the sign of any charge that we're going to actually put in there. So definitely now we can see that since the magnitude of these q's is positive, and of course if you always square a number, that's always going to be positive, that we have a positive magnitude in the x hat plus y hat direction, which is shown here. So we found the electric field, but if we want to find the force on a charge, then we actually need to multiply by that charge. So for example, if I ended up putting a charge here finally, and I called this charge as a, let's say Q2 is equal to a minus Q, right? Or actually, let's make it even more interesting. I'm going to call it a minus 5Q, right? So we're going to put in some other charge in there but it's a negative charge. Then all I need to do is to say that the force on my Q2, as from the other two charges, is then going to be equal to E total at that location times 5Q. So it seems pretty straightforward at this point. Oh, thank you, I almost forgot. This is times minus 5Q, which is the strength of our charge Q2. So finally, I can add up all these together, put them all together by multiplying, and you'll find that I have a minus K. Let's put our constants out in front here. Oops. And we'll have a minus 5Q squared, 5KQ squared over d squared in the x hat plus y hat direction. So just in case you're not familiar with this x hat and y hat notation, x hat is a vector that's 1, 0, right? So that's in the xy plane over here. That's the direction it's a unit vector in the x hat direction. It has length 1. Whereas y hat is equals to 0, 1. So this is the y hat vector here. And also just has the length of 1. However, when we add the two together, for example, x hat plus y hat, I could actually write that as 1, 0 plus 0, 1, and I end up getting 1, 1, right? Which is the same thing as this x hat plus y hat. So there's different notations or different ways of thinking about things. And if you ever wanted to figure out what the length of a vector is, then all we need to do is basically just add up all the elements of the vector squared and take the square root. So for example, if I have a vector that's equal to x hat plus y hat, then if I wanted to take the magnitude of this vector here, then I could simply just write square root of x squared plus y oops. I'm going to take the square root of the x hat plus the y hat component. So of course in this case the x hat component is 1, y hat component is 1, and I would do the square root of 1 squared plus 1 squared, or the square root of 2, right? So actually this is like having a, how do you say, a right triangle of 1, 1, and the square root of 2, which you also probably know from the Pythagorean theorem. So essentially, we're just making a more fancy way of thinking about triangles, which is something we've already known. But we're writing in the language of vectors, which is just meaning a magnitude and a direction. Okay, so I think that that's good for now. We've practiced using Coulomb's law here. So when I refer to Coulomb's law, I'm usually either thinking about this force law or the electric field, which then leads to the force law. So I'll write up here Coulomb's law, and we use it to find the electric field at a given point, which then ultimately allows us to calculate the force on a charge. In some cases, you're asked to plug in some actual values. So sometimes we'll use this value for K. So sometimes K is a constant. 9 times 10 to the 9 newtons meters squared per coulomb squared. And so the charge is usually given in coulombs. And so, for example, the charge of 1 proton would be equal to 1.6 times 10 to the minus 19 coulombs. And the distance might be given in centimeters, but we need to convert into SI units. So, for example, if we had a distance of, let's say, 3 centimeters, then we'd have to say 0.03 meters. So hopefully you can see at this point that if we have all these put together here, I'll have my K, which is in newtons meters squared per coulomb squared, my Q, which is in coulomb squared, so it looks like the coulombs are going to cancel out, and the D, which is in meters, and so you have a meter squared at the top and a meter squared at this bottom here. So we end up being left only with newtons, so we end up getting a force which is in newtons. I think that's probably about good for now. That's using the vector addition of electrical forces in a plane to figure out the total force on some charge. Thank you.